Mass spectrometry, hydrocarbons. In alkanes, fragmentation tends to occur toward the middle of unbranched chains rather than at the ends. Also, generally, the more stable carbocation is formed in preference to the more stable radical. Now let's do a comparison between branched and unbranched alkanes. Under unbranched alkanes, we are going to take octane as an example. Under branched alkanes, we are going to take a highly substituted alkane, 2,2,4-trimethylpentane. Now in the case of octane, you can see that a series of cations is formed differing by 14 atomic mass units. So as you can see from here, there is a peak at 85 and there is also a peak at 71, which corresponds to the loss of CH2 group. And also, you do not see any fragmentation of the CH2-CH3 bond. Say, for example, this bond doesn't break at all. If it's going to break, then you will see a peak that corresponds to the methyl cation and another one for heptyl cation, right? But you do not see any peak that corresponds for this C1-C2 bond breakage. When it comes to the branched alkanes, the fragmentation is going to lead to the formation of secondary and tertiary carbocations. If you take a look into the structure right here, we are going to find out the most stable carbocations that are formed. From the mass spectrum, it's very clear there are two important peaks, right? So this peak is definitely going to be the base peak, and it should definitely correspond to the most stable fragment. So this is going to correspond to the tertiary carbocation, which is the most stable fragment that is obtained for 2,2,4-trimethylpentane. And apart from that, there is also a peak at 43, which corresponds to this secondary carbocation, isopropyl cation. And also another thing with respect to the branched alkanes is that you are not going to see a molecular ion peak. The molecular ion peak is missing because we know that the molecular weight of this compound is 114, and you don't see a peak for the M/Z value of 114 here. Cycloalkanes. The most common fragmentation patterns of cycloalkanes are loss of side chains and loss of ethylene molecule. Let's do this with an example. We have methyl cyclopentane here, whose molecular weight is 84. From the mass spectrum, it is very clear that we have the molecular ion peak, which has an M/Z value of 84. And we also see two important peaks here. The peak at M/Z value of 69 is going to be corresponding to the loss of methyl radical, resulting in the cyclopentyl cation. And the peak at M/Z value of 56 is the base peak for this mass spectrum, and it corresponds to the release of ethylene molecule. When there is a one carbon cleavage, the fragment resulted with odd mass number. When there is a two carbon cleavage, then it resulted in the even mass number. Alkenes and cycloalkenes. Alkenes generally show a strong molecular ion peak, which is formed by the removal of one pi electron from the double bond. As you can see from here, this is the mass spectrum of 1-butene, which has a molecular weight of 56. And from the mass spectrum, it's very clear that there is a very strong molecular ion peak existing at M/Z value of 56. And apart from that, there is also one other peak. The peak at M/Z value of 41 is the base peak. And this is due to the formation of resonance stabilized allylic cation. For example, if this methyl group is going to be lost, then it's going to result in the formation of the allylic carbocation. And we know that the allylic carbocation are resonance stabilized. When it comes to cycloalkenes, the fragmentation of it is going to give us 1,3-diene and an alkene. And this process is basically the reversal of Diels-Alder reaction. So here is our 1,3-dienyl cation, radical cation. This is a radical cation. Like alkenes, alkynes also show a very strong peak for the molecular ion. And one of the most important peak in the case of alkynes is the resonance stabilized propargyl cation, which normally occurs at M/Z value of 39 in the case of unsubstituted propargyl cation. Aromatic hydrocarbons. The aromatic hydrocarbons also produces an intense molecular ion peak. Here is the mass spectrum of toluene, which has a molecular weight of 92, which is an aromatic hydrocarbon. And as you can see from the mass spectrum, it's very clear that the molecular ion peak here is very intense. The mass spectra of toluene and most other alkyl benzenes are going to show a fragment ion at M by Z value of 91. Here also you see a base peak at M by Z value of 91. While we may be thinking that this peak at M by Z value of 91 corresponds to the benzyl carbocation, experimental evidence says that it corresponds to the tropylium carbocation. In tropylium carbocation, this positive charge is distributed evenly on all of these 7 carbons and therefore it's said to be more stable.